is Michael McRonald. I am part of Team 26 for the class EE489. I'll be going over the solar charge controller for modular MPPT implementation. Now, to get everything started, for the project introduction, the whole point is there's a growing demand for renewable energy. Managing the energy for unpredictable sources is increasingly important. And the existing charge for controllers often lack the power handling the advanced features needed for remote controllers. Now, maximizing the power output under fluctuating sunlight and constantly charging the current and the voltage limitations is what this device is made to do. Now, the goal of this device is to solve with a robust off-grid charge controller that can handle large batteries, log data, incorporate error correction, and remain affordable. That's the most important part. It will prioritize system longevity, battery protection, high efficiency to the 95th percentile with flexibility for different battery types, and the MPPT charging for optimal power use. Now, the project purpose is for existing challenges like limited direct comparisons to MPPTs, the inefficient and unreliable power controllers in consumer sources today, the high thermal dissipation and bulky designs for current MPPTs. The project contribution will be improved energy conversion and compact design, modular MPPT implementations to streamline the testing and the innovation. Now, for the design elements, we have four main focuses for the functions: the battery protections, the voltage regulations, the maximized power point tracking, which is MPPT, and then lastly, the load management. These are the key features we'll be implementing in our design. Thank you.
Hello, this is Logan Anliker, and I'll be covering the technical specifications of the project. So our solar charge controller features currently supports 15 to 60 volt panel input and 12 volt and 24 volt battery systems. Preferably, this was to identify and prove the data behind the efficiency of gallium nitride and other components, and hopefully in the future we're hoping that the confirmation of this will lead to a scalable, larger input and outputs. But confirming the efficiency, we have the MPPT implementation tracks the maximum power output by adjusting duty cycle of the buck converter, handles the variability in temperature and shading. We have the important hardware functions of the gallium nitride, which is high frequency switching for efficient conversion. We have a compact design, reduces the PCB size and improves thermal performance. The microcontroller unit manages systems, signals, and battery protection, reads all the data. The voltage sensors monitor panel and battery voltage. Synchronous buck converter, this steps down the solar panel voltage as well, maintains constant current or constant voltage for efficient charging. Current sensors measure the flow from the solar panel for safety management, and then temperature sensors just to make sure that it's not overheating. Our key project theory, we have MPPT as the backbone of the project. It's just for optimal voltage and current, assuming efficiency within the entire system. Gallium nitride for higher efficiency and reduced thermal dissipation and smaller PCB size. And then the overview is just ensure safe and optimized operation.
My name is John Corral, and I belong to EEE 489, Team 26, doing the MPPT solar charge controller. I'm going to cover slides 8, 9, and 10. Starting off with slide 8, this is the MPPT methodologies slide. What we're looking for, the basic MPPT, is estimating the global maximum power point range. We want to identify the peak operating conditions based on the voltage and current. So whatever environmental conditions that are provided to us, whether it be shaded, overcast, we want to find the point of max efficiency in production. When we look at the advanced MPPT, perturbing voltage, considering the resulting differentials, incorporating open circuit voltage and predictive algorithms. Project goals, We wanted to take a deeper comparison of the MPPT methodologies, constructing single physical charge controller, executing differential MPPT algorithms, and trying to enabling real world analysis. Okay, looking at the charger state machine, the behaviors, we of course want a standby mode. This is an initial state of the charge controller. We're going to be looking at a bulking stage, beginning charge stage. This should account for 70% of the stored energy that's delivered. Then we're looking at a topping stage. This is like a boost stage. This is where the remaining 30% is delivered at a constant voltage, but with the falling charge current. Then we'll have an equalization stage. This is going to be beneficial to like lead acid batteries, things that need to be controlled from being overcharged. And then a trickle charge, of course. Over time, as the battery depletes, you can recharge it up. And last slide here is just kind of like a block diagram of our state machine and how the behavior should be acting. Thank you so much.
Hi, my name is Gerard Souza, and in this part I am going to be going over the results sections for our MPPT controller slash optimizer. So first I'm going to go over the testing parameters, which is basically outlining the specifications of our board. We have the open circuit voltage, the short circuit current, that's basically saying, hey, we're going to be operating our PV cell at 45 volts at 6 amps. The MPPT voltage and current is basically saying once you turn on the once you start the algorithm, you're going to be operating at 36 volts at 5.5 amps. Initial voltage will be starting at 36 volts, basically the lower delta bound for the when the voltage the MPPT algorithm starts, and so on, increases or decreases. And then the voltage step is 0.5 volts, which is basically saying, hey, this is what we're going to be optimizing for if we want to increment or decrement the voltage. Temperature and irradiance are going to stay variable as needed. So next slide. And next slide is our algorithms chosen are basically incremental conductance, perturb and observe, and constant voltage. Incremental conductance is basically just taking a certain time interval where you take the power and voltage at that time interval and just taking the derivative of the power versus voltage. Perturb and observe is basically an iterative process where it takes it's basically reflects t minus 1, looks at the previous time and basically takes the power at that time and optimizes for whether or not the power was greatest out of what's recorded. And then constant voltage is basically recording the voltage at the starting time interval, and then using that as a target to keep power to have the P versus P times I power equation modified. Results, our test case for our results are a standard test condition where you operate your PV cells. What's rated at, basically your PV cells are rated at irradiance, where irradiance is basically the amount of energy per surface area, and then temperature, and that's it. So we have a standard test conditions. Morning evening conditions, basically what you expect on a normal day-to-day basis. Hot summer day is basically a summer in Arizona. Cold winter day is basically what you'd expect on an average. And then partially cloudy conditions is basically an average of a hot summer day and cold winter day, and the average of the amount of power required on the lower section, and then the temperature also is on the lower end, but an average of that. Extreme cases we're not going to be testing for our project here today. Reflecting on the results, so first we recorded a baseline test. So this is basically going back to our standard test conditions, where we wanted to actually just look at, this is not really important, we are just trying to look at our baseline metrics and then trying to see where we stand in terms of the amount of power we consume. Are we consuming the rated power, and what's the efficiency expected? Normal day-to-day night conditions is as discussed, what you expect on an average. Hot summer and cold winter days are the extremities, and basically cloudy conditions is the average of the extremities. So concluding our results, the general takeaways is that the baseline metrics proves the baseline metrics were the worst in comparison to the MPPT algorithms as seen before. We are usually seeing a 50% efficiency figure for across the board across all test cases. Incremental conductance was our best performer, usually averaging around 95 to 99%, and an average 98% efficiency. Constant voltage was our most struggling algorithm, where we had the lowest efficiency, but we occasionally had better power consumption. Better power consumption as in better power output, but the least efficiency. And then the patterns found with our test cases was that as expected, hot summer day, we saw the most power generated at 239 watts and 242 watts actually, and but consequently efficiency dropped at 2 to 3%, as you change test cases to the extremities, and depending on the algorithm you're running. And inversely, cloudy days and low temperatures recorded the highest efficiency. So you would notice that the efficiency figures are better on a cold winter, and though we had the highest values on a hot summer day, the averages on a cold winter day and a cloudy day, you would see better efficiency figures. And then and then constant voltage was also recorded at its best numbers during those test cases. So yeah, that's our result sections.
Hi, I'm Joseph Sherporn. Our team chose the TIDA 010042 reference design for the basis of our charge controller, as the design and accompanying firmware are available for development. The device uses GanFET switching technology, and the MPOM 1506 ARM processor it utilizes provides adequate processing power and an array of originally superficial input points to accommodate the desired improvements. While the reference design included many of our must-haves as far as charger functionality already, it was necessary to fully understand its workings in order to blend our additional inputs and firmware updates with the existing functionality. The modular MPPT charge controller achieves high efficiency charging with a reduced footprint and decreased material cost versus traditional MOSFET charge controllers. Both of these significant value adds are facilitated by the decrease in peak power through many of the components provided by the increased switching speed. Additionally, users may implement MPPT regimes of choice with the firmware now preloaded with the more simplistic schemes. The modular MPPT solar power controller contributes to increasing renewable infrastructure robustness by pushing reliability and lessening typical contributions to wear and tear on device. Increased longevity results in lower lifetime costs and higher user confidence. The modular capability of the PowerPoint tracking implementation encourages further study of means for improved efficiency and provides greater options for tools to do so. Thank you.